All right, ladies and gentlemen, here we are with Unit 5 Aqueous Chemistry. Today in this video we'll be looking at the single replacement reactions, which, as they might sound, are very similar to that of a double replacement reaction, but only one thing is being replaced. There is also some things that we will need to make sure that we use, and that will be the back of our periodic table, so hopefully you have one of those. First thing, probably one of the more difficult, or at least some people find it difficult, and that is the oxidation reduction, the terminologies that are involved with this. And I think a lot of it comes, and it was, in a lot of times, chemistry teachers, we use the red ox as the way of doing it, and that is a reduction oxidation. Redox reactions is sometimes what we call them with that. But when we look at redox reactions or oxidation reduction reactions, we'll kind of use either or with both of them. And with that, we will see that we have, where does this actually happen? Is an oxidation occurs when an atom or an ion loses electrons, and a reduction is when it gains electrons. That's very counterintuitive, and that you see this reduction is a gaining of something, and that's usually not common. When we say reduction, our brain automatically goes to losing. Now, reason why it's confusing is we understand that in the atom, of the three main subatomic particles, the electron, the proton, and the neutrons can change and can vary from atom to atom. The electrons can vary from atom to atom and for ion to ion, but the protons stay the same. But if you look at these two terms in the manner of the proton, the definition actually makes a little bit more sense. But we have to remember that protons don't actually move. They stay where they are, and it's because of the electrons moving that allows this to, or potentially kind of really confuses some things with that. And so if we look at the oxidation occurs when an atom gains a positive charge, and reduction is when an atom loses a positive charge, the terms make a lot more sense. But we don't, how does one lose a positive charge? Well, it loses a positive charge by gaining electrons. And so those are little things that we have to really kind of think about, and it's very important that we utilize those understandings of, okay, losing electrons increases the positive charge, gaining electrons decreases the positive charge, and we should have that, and that's why, again, it's been built upon up to this point. And so we do want to make sure that we have that down, because that is usually where the confusion lies. Well, a single replacement reaction, or sometimes we're called redox reactions, involve an element essentially replacing a metal. So it's metal to metal. Now, you can have non-metals replacing other non-metals, but that usually is only for group 7. That is usually, again, non-metals can be replacing non-metals, but that is only for group 7. Traditionally, there can be others as well, but we are really only going to focus on that group 7 because they have an activity series, which we'll look at in just a little bit. How do we know which one's going to replace which one? based on how they're written. So the way they're written on the periodic table, fluorine is the most reactive, and then you go all the way down to iodine at the bottom, and that one is the least reactive with that. Now, they have the general equation that M, which is a metal, can replace N, another metal, to make the general equation. And this is again another some of those ones where you have the general equation. Hopefully you also have the general equations from synthesis reactions, double replacement reactions, decomposition reactions, combustion reactions, and so now you have the potential of having those tests where they'll say which of the following general reactions form this, or which one of the reactions is this type of a reaction. You have to be able to look at the reactions themselves and determine that. And so some of these things are what you're going to see within these types of reactions. But how do we know whether or not this happens? That's the thing, is if by looking at it, you'd have a very difficult time. Experimentally, we would be able to do that, and we actually have an experiment that we do in class that shows this. Well, in the lab, and you've actually done this before, earlier in the unit of, let's see, I think it's unit 1, when we were identifying whether or not chemical reactions occurred or not, is that you placed, it wasn't an iron hook, but it was a steel wool, and you put it in a solution of copper 2 sulfate, usually a bluish color of a solution, and it turns kind of darker, and then eventually it starts to look as if the copper's coming out of the solution. Now, you also did this in the copper recovery lab, where you had the green solution of the copper 2 chloride, and then you put the aluminum in that solution, and you recovered the copper out of that. Now, both of those reactions are essentially almost the same thing, just in this case we had iron replacing copper. In the other one, we had aluminum replacing copper in that reaction. Now, the reverse would not happen, and that is, you would not, if you put copper in a solution of, say, iron sulfate, you would not, any type of iron actually, I just have iron 3 as the example here, you wouldn't actually see the reaction happen. It just does not happen. There are no reaction NR, writing out no reaction. I prefer the no RXN. That's just what I used when I was in high school and in college to do that. And so you have a lot of different options. I think your homework in Mastering Chemistry usually has you write out no reaction with no space, and so that's just for them and their coding purposes. But some of these will not happen, and so being able to look at, say, the back of your periodic table in the activity series, or looking at an activity series, will be very beneficial. So again, you have an activity series for my classes on the back of your periodic table that you should not have to frantically write all of these down. They're very easily found usually as well. There might be some changes here or there between which ones, sometimes they show chromium, sometimes they don't show chromium, but usually most of them do. It's like hydrogen is usually another one that's kind of a where is hydrogen at, and a lot of it comes down to some of those things. And you can actually see that they have the net ionic equations written out here, because it doesn't matter what it's going to, it's forming in that solution, and that they're all losing electrons, so they're all being reduced. And they're all oxidized because it reduces a gaining of electrons. I'm sorry. So what do we look at this? It's like a popularity chart. That lithium is the most popular element on the periodic table. All the non-metals, and polyatomic ions, they want to dance with lithium if they can. And so what we see here is, say, if a compound was dancing, so you have a non-metal, let's just use chlorine for example, is dancing with zinc. The zinc is less popular than lithium. If lithium is added to the mix, so to speak, chlorine will leave zinc to go dance with lithium. And in that process, zinc comes out of solution in that process. And so you start to get that lithium chloride then forming. Now, if you had, say, zinc was in dancing with chlorine, and copper was added to the solution, nothing would happen. Chlorine would not go and react with or dance with copper because it's already dancing with the more popular element. And so you can look at it in that way. It's not very nice, but that's socially, that's usually how it happens, is that it's a kind of, you want to dance with the more popular person, the best dancer. And so what you're looking at is that, in that if you have something by itself that is more popular than the thing that already has a dance partner, the dance partners are going to switch out. That's how I usually use. It's a good analogy, I think, that we all usually get, like, oh yeah, I would rather go dance with the more popular person or the better dancer than sit by myself and do nothing, or dance with somebody who's not as good at dancing or as popular, for whatever reason. But that's how I utilize it. And you'll hear me reference it as well as we go through. So in this first example here, it says predict the following reaction will occur or not. And so now we need to look at, and we can even determine whether or not this is going to happen right off the bat, is we look at it and say, is sodium more popular than potassium? Well, potassium's number 2 on the activities here, so it's the second most popular cat out there. So potassium is not going to be replaced. Sodium cannot replace potassium in this reaction, and so what we actually end up seeing then is just no reaction. It just doesn't happen. And so you're like, okay, that's lame. And so what this predictability allows us to do is actually predict a lot of things before they even occur, and then go into the lab and potentially sometimes change whether or not this is actually going to happen. Now here's another example. Magnesium and zinc are put in solution, and so we look at where is magnesium, make sure you don't confuse it with manganese, and where is it compared to, say, zinc. Well, zinc is below magnesium, okay? And so because zinc is less popular than magnesium, magnesium is going to replace zinc in this reaction. Now, one of the things that we have to make sure that we pay attention to is pay attention to charges. Because this is going to definitely be something that we see a lot with this, because we need to be able to look at and say, where did this 2 come from? It came from zinc, and so that's where we can see, but it doesn't actually form that. But what it helps is kind of like knowing where it all came from. And I usually like to write my metals out by themselves, and so we would have zinc and solid, and then that is going to react with, then on the product side, magnesium. Now magnesium, if we look on the other side of our periodic table, or if we just know that magnesium is in group 2, it has a positive 2 charge, So in this case, my charges are kind of flipping and flopping on this, and sometimes that happens, and that's really nice when that happens. And so that our reaction then becomes balanced as it's written. And so we need to make sure we pay attention to those charges. And so then we have that. Is it balanced? Yes, it is. And so we're able to move on. Now, in the next reaction, we'll see that we have lithium, the most popular cat out there. It's the cool cats, the cool guy or cool kid or whatever. And gold, very unreactive actually, because it's usually always found as itself. It's usually just found by itself in nature. Some people would say, well, I would much rather dance with gold than lithium. We say that now, but I have a feeling like in the future, lithium is going to be very valuable because of how we use it in our everyday lives for our iPads or cell phones, and anything that requires a lithium ion battery. I think that's going to make, unless we come up with an alternative, the lithium could definitely have that with that. So we have some of these things with it, and so we know gold is going to get kicked out of this one, and so gold is going to be hanging out by itself now, which is normal because that's what we see. And then lithium is going to react with the sulfate. Now, when we look at where did this 2 come from, it came from sulfate. Again, paying attention to those charges, and we got to make sure that lithium is in group 1, therefore it has a positive 1 charge, and those charges don't match up, so we crisscross, and then we jump, and put our SO4 like so, and that is an aqueous solution, as we would have. Now, this is not balanced, and so what do? Well, we balance our chemical reactions. One of the nice things about this sometimes is that our reactions will balance out very nicely by just putting in a couple numbers. Sometimes they don't, but sometimes they do. So, and therefore, now we have it balanced. Now, predict the following reaction, whether or not this will occur. And so here we have cobalt is dancing with iodine, and more specifically, cobalt-3 is dancing with iodine. And then we are looking to see whether or not where is lead on the activity series or the popularity chart, so to speak. And lead is below cobalt. So, because cobalt is more popular, it will have no reaction with this. Now, there are some ones that, with the acids, that you have to be very careful with, that some acids will react with a metal that it isn't, and so we do need to be a little bit careful about that. And that's why a lot of times we like to go into the lab, and so that you can see some of these. That's, why did we use, say, like a hydrochloric acid to react with some things, or a nitric acid? Why did we put copper into nitric acid originally? Well, that's because nitric acid will work and have the solution, make the copper 2 nitrate solution, and hydrogen gas is given off. If you used hydrochloric acid, it wouldn't react. And so we have to be careful about that. And how we know that is through experimentation, experiencing chemistry, experiencing science. And so next time we will go into the lab, and we will do some single replacement reactions. If we think that hydrogen gas is being given off, we will trap that hydrogen gas, and we will do a kind of the flaming wood splint test to see and check for that, because if it does have hydrogen given off, it will bark for us, and that will be one of the indicators that hydrogen gas is being given off. And so we can identify some of those things. So as we continue forward, we will keep using these things, keep using these analogies. You should be able to get through a lot more of your master in chemistry now. There's some calculation stuff that isn't going to be allowed, that you can't really do quite yet. But that's one of the next things that we're going to start looking at is some of the calculations that are involved in this unit. But after this, we should be able to do a lot of your master in chemistry. And we will also, again, go into the lab and do the single replacements reactions lab. So until next time.